Hey, Algebra 2 Honors. This is going to be Unit 8, Day 6. Today we are talking about working backwards. We've done this in the context of quadratics. If you look back in Unit 7, the idea today is going to be if I gave you the roots of an equation, how do we come up with what the equation is? So to review what we already know about working backwards, here's a quick recall. Write the equation of a quadratic whose roots are 2 plus or minus 3i. And I hope this isn't too far from your memory banks here, because this was just in Unit 7, where in order to figure out the equation given those roots, you might have considered calculating the sum of the roots and then the product. And that's how I'm going to approach this. So if the roots are 2 plus 3i and then 2 minus 3i, adding them together gives me the sum of the roots. Those I parts will cancel out. And then the product would be another coefficient that's in the quadratic equation, 2 plus 3i times 2 minus 3i. And we know that when we get that conjugate pair, we can just do the first times the last. So that's going to be 4 minus 9i squared. Since I squared is -1, that becomes 4 plus 9, which is 13. And now that we have the sum of the roots and we have the product of the roots, as a reminder to write the equation, you would write x squared, change the sum, so minus 4x, keep the product plus 13 equals 0. And that is a really quick refresher on how we write the equation of a quadratic given the sum and product of the roots. So in general, we know that it's x squared, change the sign of the sum, that's the coefficient of x. And then the product is the last coefficient right here. So here's what it is for a quadratic. Well, today you can imagine that now that we're in a higher order polynomials unit, we're going to extend this for the patterns for a cubic polynomial. So cubic polynomials have that one extra term, right? 3 terms in a quadratic, we get 4 terms in a cubic. So let's just see how this process is going to change a little bit when we extend this to a cubic equation. We're going to have x cubed. You're still going to take the opposite sign of the sum, and that's now the coefficient of x squared. So no matter what, you will actually always take the opposite sign of the sum, but that gets moved up now. And I'll tell you, the product is still the thing that's going to go at the end. So what goes as the coefficient of x is you're going to write plus the sum of the products 2 at a time. And that's a really lengthy name for the name of this coefficient of x. And I think even just reading it makes it even sound a little bit confusing. But when we get into practice with given roots, we'll make some sense of finding the sum of the products 2 at a time. And like I said, the product will go at the end. But what we'll find for the signs is that they alternate down the line. So x cubed, we're keeping it positive. We change the sign of the sum. You're keeping the sum of the products 2 at a time. So what that means is that you're going to change the product. And just remember to set that equal to 0. So whereas the product's sign stays in a quadratic, the product sign will change when we talk about writing a cubic polynomial equation. Let's start with some really easy examples. Like, let's start with a practice problem where the roots are, let's make it as easy as 1, 2, 3. Just so we can see when I find these different elements, how that all breaks down and fits into the equation of a cubic polynomial. Now we know in the end we could actually do x minus 1 times x minus 2 times x minus 3 to check this and multiply all that together. But I think that when the roots get complex and irrational, you're definitely going to want to default to these ideas of sums and products. So let's find the sum real quick. The sum would be 1 plus 2 plus 3 for a total of 6. So that's pretty easy to find. I'm going to go in order. So the next thing I'm going to find is this thing called the sum of the products 2 at a time. And to denote that I'm finding that sum of the products 2 at a time, I usually write that as sum 2 with a little subscript of 2 there. So what sum 2 means is I'm going to take the roots 2 at a time, find the product of those roots 2 at a time, and then add that whole list up. So let's see what that looks like. If I take the first root and the second root, take the 1 and the 2 and multiply them, that would be 2. Then I'm going to take the 1 and 3 and multiply those, and that would be 3. The last pair you can make here is the 2 and the 3, and that would be a total of 6. So what I'm going to find is the sum of the products 2 at a time. Hopefully looking at it with these concrete numbers helps to make some sense as to what that actually means. Well, 2 plus 3 is 5, plus 6 is 11. So the sum of the products 2 at a time, that coefficient of x is going to be 11. Last step is to find the product. The product is all 3 at once, 1 times 2 times 3. And coincidentally, that also comes out to be 6, just like the sum. Of course, those won't always be the same, but just coincidence that it works out that way. So putting everything together here, if we have this is my sum, sum 2, and then product, your equation would start off as x cubed. We're going to change the sign of the sum, minus 6x squared. Keep the sum 2 at a time, plus 11x. And then finally, change the product and set that equal to 0. So if it helps, eventually what I may write underneath here is you're always going to keep x cubed as is, but then you change, then you keep, and then you change. So alternating down the line, you go keep, change, keep, change. And if we go out even further, you're going to see that pattern extended even more. Okay, let's try another one where we throw in some complex roots, like we started today with the quadratic example. If the roots are 2 and then 1 plus or minus I. Let's figure out what the cubic equation is that has those 3 roots. So if we find the sum first, 2, 1 plus I, and 1 minus I, that would all add up to 4 because the i's will cancel, and that should always happen. Okay, moving on to the sum of the products 2 at a time. This might take you a little bit longer to get used to, but I promise by the end you'll start to feel pretty confident about it. All right, 2 times 1 plus I is 2 plus 2i. Just distribute the 2 in there. Then you compare 2 with 1 minus I. So that's going to become 2 minus 2i. And the last product is 1 plus I and 1 minus I, that conjugate pair. So that's going to become 1 minus I squared, right? First and the last. If I squared is negative 1, 1 minus negative 1 is 1 plus 1, or 2. We're going to find the sum of these products 2 at a time, which is a total of 6. 2 plus 2 plus 2. Okay, so for the product, we have to do all 3 at once. 2, 1 plus I, and 1 minus I. We already know this product, though, so be smart about your work. If we just did 1 plus I times 1 minus I over here and got 2, that's going to really quickly help me get that the product is 4. So you're going to see that happen a lot, that whenever you get these conjugates multiplied, that may come up in other coefficients that you have to find. So just use that knowledge and kind of carry that over to other coefficients as needed. So this is, again, coincidental. Sum and product come out to be the same. That will not always happen. But when I go to write the equation, we would write x cubed, change the sum, so minus 4x squared, keep the sum 2 at a time, plus 6x, change the product to minus 4, and of course, set that equal to 0. Okay. So that's pretty much it. If you understand this new concept of sum 2 at a time, working backwards with cubics is not all that different than with quadratics. I am going to have you try one on your own that we'll recap next time. I'm going to give you roots of negative 4, 1/2, and 3. Now, I am challenging a little bit here on your own because we have a fraction in the mix. And what that might mean is you might get some fractional coefficients for sum 2 at a time, maybe product. Make sure in the end, if I were to come around and check your work, I want to see that your equation has integer coefficients. Don't give me any fractional coefficients out front, okay? So make sure you work on that by the next time I see you. Get the equation, sum 2, product. But if you have any fractions out front, I want you to fix that and think about how we do that from the last unit. Okay, let's move on and talk about 4th degree polynomials. Fancy name for those are quartics. So the pattern for a 4th degree polynomial, if you want to find the equation given the roots, is the following. You're going to start with x to the 4th. You're going to then change the sign of the sum, and that goes next to x cubed. Maybe no surprises yet, right? We're always going to change the sum. Then you're going to keep the sign of the sum 2 at a time. That's going to be the coefficient of x squared. That sum 2 at a time is what we just did with the cubic polynomial. It's the sum of the products 2 at a time. Here's our new coefficient. Our new coefficient is going to come in as the coefficient of x. Now I keep, change, keep. I'm up to change now. We're changing, and it's going to be the sum of the products 3 at a time. So instead of taking pairs of roots and multiplying them, we're going to take a group of 3 roots at a time, multiply all 3 of those, and find that sum. Now, since I did keep, change, at the end, we're going to keep the product, and that's going to equal 0. Okay, so keep, change, keep. We have an extra coefficient we have to find, a little bit more involved in our process, but let's get right into it with the following roots. If I gave you roots of -3, -2, 1, and 2, let's see if we can find the sum 2, sum 3 product and put it all together in a nice 4th degree equation. For the sum of the roots, add them all up. -3, -2, 1, and 2. So when I add those up, let's see, the 2 and the -2 cancel. So 1 plus -3 is a sum of -2. Okay. For the sum of the roots 2 at a time, if you have a cubic polynomial, 3 roots, there will only ever be 3 combinations for the sum 2 at a time, right? There was 3 possibilities here, 3 possibilities here. But if you have 4 roots total, there's going to be a few more. There's actually 6 combinations. So you might want to make a note of that here. For a 4th degree, the sum 2 at a time has 6 combos. All right, here we go. Let's see if we can find all those combinations. It's going to be -3 and -2 multiplied. Then -3 can get paired with 1. And then -3 can get paired with a 2 at the end. So I start with the first root, pair it with the other 3. Then move on to the next root, -2. Pair that with the 1, and pair that with the 2 at the end. And the last pairing that we have not accounted for is just the last 2 roots paired up. 1 times 2. And if you count down the list, you should have a total of 6 that we're going to add up here. All right, let's see what these products are. It would be -6, -3, -6 again. Oops, sorry, that's +6 to start. Better double check that. +6, -3, -6. That's -2, -4, and 2. And the nice thing about this is that there are a fair amount of things that cancel. 6 and -6 cancel. -2 and +2 cancel. So it looks like we have -3 plus -4 for a total of -7. Okay. We're ready for our new coefficient, which is the sum 3 at a time. The sum 3 at a time, if you have 4 roots and we want to choose 3 of them, there are 4 combinations here that we will need. So 4 roots and we want to choose 3. So let's see if we can get all 4 combinations. -3, -2, and 1. The first 3 roots. I can do -3, -2, and 2. I can do -3, leave out the -2, and then do 1 and 2. So -3, 1, 2 is the third combination. And right now I've found all the combinations of -3 with 2 more roots. So actually the last combination is leaving the -3 out. And we have the last 3 roots, -2, 1, and 2. So we're going to find the products 3 at a time, and then whatever those products are, find that sum. Add them up. So the first product, -3, -2, and 1 would multiply to +6. The next one would be 6 and then times 2, which is 12. Then it looks like we're going to get -6 here. And at the very end, -4. So the 6 and -6 cancel. And we're going to get 12 minus 4, which is a total of 8. So I've got the sum 3 at a time. And finally, the last thing I need is the product. The product is all 4 at once. -3, -2, 1, and 2. It's also kind of the sum 4 at a time, if you want to think of it that way. But the product is just all 4. So that's going to be 6 times 1 is 6 times 2 is 12 for the product of all of the roots. So now that we have all of the coefficients, we just have to figure out which ones are we keeping, which ones are we changing, and the pattern does alternate. Keep x to the fourth always, then change, keep, change, and by the time I get to the last, we're now up to keep. So we're keeping x to the fourth. We're going to change the sum, so plus 2x cubed. Keep the sum 2 at a time, so minus 7x squared. Change the sum 3 at a time to minus 8x. And then at the end, we're going to keep the product plus 12 equals 0. And to save time, I won't check this, but how could I check it? Well, I guess I could go to my calculator, type that in, and confirm that the roots are -3, -2, 1, and 2. We can double check that those 4 roots go with this 4th degree polynomial. Okay. Let's do one more for practice just to make sure we're kind of on the right track with our 4th degree polynomials. In the last example we'll take a look at, let's go with roots of -1, 4, and then 2 plus radical 3. Okay. Now, sometimes Mr. All likes to get a little tricky in these questions. And we saw this come up with quadratics a little bit, but what happens is if you have an irrational root, it won't be an irrational root all by itself. So 2 plus radical 3, just like with complex roots, we know that we have another root. We also have 2 minus radical 3. They come in a conjugate pair. So if I were tricky and I said, hey, 2 plus 3i is a root, we know that 2 minus 3i is another root that goes with it. So at an initial glance, it looked like this is a cubic polynomial, but because we know those come in pairs, we have to include 2 minus radical 3 in that list as well. Okay, let's start finding all our information here. So the sum would be -1, 4, 2 plus radical 3, and 2 minus radical 3, all added up. Radical 3's will cancel. Let's see, the total of 8 minus 1 is 7. That sounds good to me. Next, we're moving on to the sum 2 at a time. Remember, there's 6 combinations you can make. We can do -1 with 4, -1 with 2 plus radical 3, -1 with 2 minus radical 3. And then I would move on to the 4. 4 can go with 2 plus. It can go with the 2 minus radical 3. And finally, the last pairing would be the conjugate 2 plus radical 3 and 2 minus radical 3. So I'm going to find all those products and add them up. All right, first product, -4. Then we're going to get, if I distribute the -1, -2 minus radical 3, -2 plus radical 3. Distribute the 4 to get 8 plus, that would be a 4 radical 3, and then 8 minus 4 radical 3. These radical parts, guys, have to cancel out. You're not going to be left with a coefficient with a radical in it. All right, we got a conjugate pair at the end to do the first minus the last. So the first product would be 4 minus, that would be a 3 when I multiply these. 4 minus 3 is 1. Just be careful with that last product because this will come up in the sum 3 at a time and the end product. So we want to make sure we definitely establish that correctly. All right, if I do all the adding up here, this is a total of -8 here, isn't it, right? All those. And we have a positive 8, so all that will cancel actually. And then 8 plus 1 is 9. However you best want to combine those, but if you notice like, oh, that's a sum of -8 and we have a positive 8, you can cancel those out. Let's move on to the sum 3 at a time. Let's see if I can squeeze this in here. All right, so I have to do 3 roots at a time, so I could do -1, 4, and 2 plus radical 3. I could do -1, 4, and 2 minus radical 3. And there's 2 other combinations. I could do -1 with this conjugate pair, -1 with 2 plus and 2 minus radical 3. Squeeze that in there. And then I could do 4 with the conjugate pair, 2 plus and 2 minus. All right, don't be afraid to use, I usually have pretty big handwriting, but don't be afraid to use lots of space to do these questions if needed. Okay, careful here, but let's multiply the real numbers first, the rational versions, I should say. -4, distribute that in, so that's going to become -8 minus 4 radical 3. Let's see if I can fit that. -8 minus 4 radical 3. And then over here, you'll get -8 plus 4 radical 3, -8 plus 4 radical 3. Sorry, this is so tiny, guys. Hopefully you can see it okay. All right, we already know that these multiply to 1. So 1 times -1 is -1. And again, if this is 1, then this 1 times 4 is a 4. So that says -8, this says -8, -16, -17, and 4 is a total of -13. If I've done that correctly here, -13. And finally, the last thing I need is the product, -1 times 4 times the conjugate there. This should be pretty easy at this stage because we know that those multiply to 1. So 1 times 4 times -1 is a total of -4. Okay, putting all of the pieces together. Here we go. Last step. We get x to the 4th. Change the sum, minus 7x cubed. Keep it, plus 9x squared. Change it, plus 13x. Keep it, minus 4 equals 0. If it helps to write down that whole KC business, right? Keep, change, keep, change, keep. I think until you get really used to that pattern, I would write it down underneath and make sure that you're carrying the correct signs down. Once you do enough practice with these, it is pretty methodical, and I think you'll find that it's not such a bad process, but it's really easy to make little addition, multiplication mistakes, and then remembering the signs at the end. So keep practicing with those types of things. But of course, much more practice to come with working backwards given the roots. Have a great day.